biggest takeaway for these questions is that you need to find a way to wrap your head around them. I don't know what your plan is when it comes to solving a question like this. I have a plan. And when it comes to solving a problem like this, there's a plan that I use to employ to solve it. It's not about the question. And I want to make that part really clear here, that Newton's laws are a procedure, and at the end of that procedure, it will produce a relationship. That relationship may or may not solve your question, but that's all that Newton's laws can do. Now, you wouldn't be asked this question if Newton's laws couldn't solve it. Does that make sense? So, I'm confident that they will work. But what I mean to tell you is that you can't attack the question with the idea being that you can just throw stuff at the question that you've seen before and assume that you'll get Newton laws to work for you. That's not how they work. They are a set of procedures and have implications. If you follow those procedures, at the end, you will be left with something that you can probably use to solve for your answer. And you have to approach it different than this is just another math problem. Because if you approach it like this is just another math problem, you're not going to do well on your test tomorrow. And you're not going to do well on any of the stuff in physics, but especially with Newton's laws. There's stuff later in physics that you can just memorize. There's just going to be like, memorization kind of stuff, and it'll work out every time. Newton's laws aren't like that. So I'm going to talk about a procedure. And in talking about this procedure, there are things about it that if you take them carefully and look at them, you'll be fine. The first thing is I always believe in drawing a quick picture to give us an idea of what's happening. We have the guy on the skis, and he is holding on to a rope, and that rope is going up the ramp. There is a big banner piece of information given that he's being pulled up the rope at a constant velocity. That is the most critical piece of information that was given. Everything else doesn't matter that much. You just roll with it. But when they say constant velocity, they are explicitly telling you something about which of Newton's laws to use. And they are telling us that all the forces in this system are going to be balanced, no matter what, for every left force, a right force, for every up force, a down force. So once I know that, that stipulates how things have to happen. Now, there's more to this, but understand from this point forward, there's not like a random number of possibilities here. There is one answer. But to get to that answer, you have to recognize that now that I know that it's a constant velocity, I am in a very rigid position. I have to determine all the forces that are acting on the object so that I can use this to my advantage. If I leave one of these forces out, everything's wrong. So identifying what forces are acting in my system, that's kind of critical. But you've probably learned at this point, there's only like 6 forces, maybe 4 that show up in any of our problems. And they're grouped into 3 categories. There's fundamental forces, there's contact forces, and there's resistive forces. Now, these categories and these names, I just made them up. There's lots, every book has a different way of doing this, but my goal here is to organize you into a set of procedures that you can employ the same way every time and achieve the results that you want. So what we're going to do is we're going to draw a picture, not this picture, but a picture that we can work on to get our answer. And that starts with drawing a dot for a free body diagram. And I'm sure you've been talking with Mr. Mosser about free body diagrams. When we have a free body diagram, the goal here is to determine the forces acting on the system. But these forces, and the way I draw this, is not random. It has to be drawn in a very particular way. Each force has to be drawn based on the nature of that force. For example, the first one is a fundamental force, and every single problem will have one of these, so they're pretty easy. That's going to be the weight. And I will draw an arrow straight down to indicate the weight. Now, if you're going to ask me how long do I draw this arrow, the answer is I have no idea. I'm making it up. In the end, I will probably try and massage the arrows to make sense, but right now I don't know how long to make them. So I pick a size for the weight. I use the weight as my first one, and I tend to make that one, I start with that one being the biggest one, because it's very likely to be the largest force in your system. But the rest of them, I know that I'm going for balance. So as I start to draw the rest, I want to be careful to make sure that I strike a balance. There needs to be as much force upwards as there is downwards. And I'm noticing that there's going to be this pulling force from the rope. It's slightly upwards. And they're staying on an incline. The incline's pushing on them slightly upwards. So as I start drawing these arrows, I'm trying to keep that in the back of my mind. So I'm going to draw the next force, and it's going to be a contact force. So I start asking myself, what's in contact with this guy that could impart a force? Well, he's holding a rope. He's standing on a platform. Those can all impart a force. So let's start with the normal force, because there was some discussion about this all day today and even last night. Normal forces, by definition, have to be perpendicular to the surface in contact. I'm drawing this over here for just a minute to recognize that it's got to be perpendicular to the incline. That's the only way it can be drawn. I don't get to choose. So just because the last time I did one of these, I drew it straight upwards because the normal force was on an object on a table, doesn't mean a normal force is always straight up. If I am pushing against the wall, the normal force from the wall would be that way. So it has to be perpendicular from the surface. That has to be my point of reference. So I'm going to grab this force over here. Oop, I guess I can't grab just the one. So I guess I will just redraw it because that's the way things are on Shelton's iPad today. Shelton's iPad has betrayed him today. So there we go. My normal force. Now, there's a rope also attached to the guy. I'm going to have to draw that force too. And they have dictated that force. But just be aware, tension forces are always pulling forces. They always have to be in the direction of the rope or the cable or the cord or whatever it is. There's always some rope, cable, cord, string, something. So whenever you draw that, it just goes in the direction of whatever that cable is. But in this problem, it is parallel to the ramp, and we do need to pay attention to that. And I'll label it T for tension. The last one is elusive. You don't always know if you have friction or not, so it's an elusive force. So you tend to, and my students ask me all the time, well, is there friction or not? Well, I don't know. Does the problem give you a hint? Is there some way you can figure out if there's friction or not? Generally, the problems tell you if there's friction. This one's asking us to find the coefficient of friction, so there's going to be friction in this problem. But at the same time, you have to sometimes look at context clues. Like if these appeared unbalanced right now, then I'd probably have to add a frictional force to balance them out. But the important thing here is that friction must oppose motion. We've assumed this guy is going up the ramp, so friction is dictated to go down the ramp. It has to. It has to oppose motion. There's the one that you guys have with the block that's resting on a ramp and you're trying to find something about it going up or down. That's two different circumstances. There's the problem where friction deals with the block trying to go up the ramp, and then you have to do an entirely new problem to deal with the chances that the block could go down the ramp because the friction changes direction. Now, after a while, and you've developed some skills here, you'll be able to see the symmetries and simile of what was done before. You might not have to redo the entire problem, but for now, you're inexperienced and you're novices, you probably need to restart every time. And that's okay. I don't mind that you guys have a lot of work to do. Doesn't bother me at all. So, oh, Rushi wants to come in. Oh, Rushi. All you people.
It's confusing.
No, it's not. It's the same stuff all the time.
Yeah?
Hold on, let's get a Rushi in here real fast so I can make fun of her. Are you there, Rushi?
Ask her if she's at her house or in Texas again.
She's not in Texas. She's still here, but she's just a black box right now. She probably didn't expect me to let her in. I don't care.
Tomorrow you should turn around and tell your Christmas.
I'll tell you, tomorrow I'm just going to stay home. I'm done. I'm done with the whole school thing.
Yeah, same. Oh my gosh, Mr. Shelton. 8 more days.
Until what, your birthday?
No, think harder.
Halloween, I know.
No, Mandalorian.
Oh, yeah, that's far on my radar. Halloween is like right there.
Yeah, it's right after.
I didn't get to do any progress on any of my creepy stuff last night because of all the frickin' tutoring last night.
None.
I am done with this whole tutoring
What are
garbage.
you gonna do? You have so much.
Dude, I have not. I've just begun the fight.
You've just begun.
You're in the crunch time.
Till my neighbors are cowering in fear, I have not done enough stuff around my house.
I love the Zoom skeleton.
The Zoom guy's coming out good.
He's so good.
That's what I have to finish tonight. I've got to because I've got them all lit up and everything, and I've also got the thing so it flashes. It looks so cool.
That's awesome.
So, and the platform's been out in the rain for the last couple of days, so that's good though. It's getting weathered and everything. Should be able to withstand it. All right, so this is my set of forces. The next step is, like I said, and I'm telling you what I'm telling my students, but I assume Mr. Mosser has told you guys this too. I could just give you the answers, and if you want that, we could do that too. But you have to determine a coordinate system to identify how you wish to analyze the object. I have 3 rules to live by here. The first rule is if you know the system's accelerating, that's your positive x direction, period. If it's not, this one's not accelerating. So if you know what direction it's moving, that's the positive x direction. That's always a good one too. If those 2 fail you, then find all the ones that will benefit by lining them up together. Right? I have 3 forces here that are all perpendicular to each other. They benefit then by having them be the ones that tell me what direction is x and y. Because that means only one of the forces is off axis. Because whatever force is off axis, that one has to be broken up into components. That's where your trig comes in. So I'm going to do this, and that means right there, that's theta. And I don't want to go through all the geometry here. Theta will always be the one that's between the line drawn through the normal force and the weight of the object for an incline. All right, so that takes us all the way to drawing a free body diagram. You have a successful free body diagram. There's only one more thing I like to do, and that's to assign positive and negative all around my diagram here. So I like I'm going to make this direction positive x, and this direction positive y, and this direction negative x, and this direction negative y. So if you're asked to draw a free body diagram, that's it. You shouldn't do anything else to it, but this is a working diagram. We're going to use this because that's what the purpose is. And the purpose for us is to line up all the forces that are horizontal and all the forces that are vertical. We're using this. And we got one here that's none of those. It's not vertical or horizontal. So we have to break it up into its components. I describe this as wrapping a triangle around the angle, meaning start at the origin and draw a line next to the angle. And when I get down to the bottom there, turn, make a hard left, and then you have got a right triangle. The right triangle has to have its right angle against the axis. There is always some some wonderful student who makes a screw-up mistake that looks like this.
Oh, yeah.
And I just want to slap them in the head every single time. So we don't do that. The right angle goes against the axis. Now, I'm going to assume you guys can do your trig. The adjacent side is cosine. The opposite side is sine. So this is mg cosine theta. This is mg sine theta. Now, this is where I would say ultimately, you could probably just memorize that. Because unless the teacher is actively trying to screw you over, and they exist, they're out there. Most teachers know that all these things that you have to do are already a lot. And we don't need to make this harder to kind of screw you over. What we need to do is be aware that it's hard enough doing all the other little pieces. So if you have an inclined plane, you can usually count on the fact that the part of the weight that is into the ramp is going to be based on cosine. And the part of the force that's down the ramp will be based on sine. And you'll probably be able to go most of the way through, physics with that. So, like I said, unless you get one of those vindictive teachers, and they're out there, but I haven't met one in a long time. Most of us want you to do well. So we've done all the hard stuff. All the heavy lifting is done now. I'm gonna move that over here. And hello, Megan. I have no idea, who you are, but I'm glad you're here. A bunch of your friends just said hi, Megan. So you don't know who they are. They're just a bunch of masked, invaders in my room. They don't smell bad, so that's a plus. Could have been like earlier this week where the little smelly kid came in for tutoring. What?
For my picture.
That Jackie?
Oh my God, yes. I did the opposite.
Look, Megan, either turn your camera on or not, because, you know, if you're going to be talking to people in here, you can't be a black box.
Hold on, I'll hook up my camera.
Damn straight you will. All right, next.
I drew the opposite direction, but that shouldn't matter as long as I drew all the angles the opposite way, right? Like I drew the picture sort of the.
Yeah, that doesn't matter.
Okay.
Okay, so our next point, now that we've done that, to me we're on to the final step of the problem, which is actually using Newton's laws. We haven't used Newton's laws yet. Everything here is because we don't have math good enough to do 2 dimensions at once. So all of this stuff is just to make our problem 2 one-dimensional problems. So now we do that. We do exactly that. Net force in the x direction and net force in the y direction. Because it's a first law problem, it's net force in the x direction is 0 and net force in the y direction is 0. This is Megan here, so hold on, Megan. Just chill. There, all your friends they can all see you now. There, that's Megan. We don't know you, but there, now I can see you. Tell Arushi hi. She's also, you know, in the same boat as you. She's far away. She could be in Texas, but I don't think she is today. Are you in Texas, Arushi? I was told to ask.
No, I'm still in Florida.
Sorry, still in Florida. Oh, not Carlos, man. None of my students come to tutoring. Well, you guys can too.
I was gonna say, wait a
Yeah, but the Monster students are outnumbering you now.
And
I just recently realized that you did it.
No, they have a test. You guys just took a test. You should be like out like celebrating. Thank God it's over. Okay, let's finish because eventually I need to go home. So this is a set of instructions. You understand that, right? That it is not an equation. It says add up all the forces in the x direction, taking into account their direction, and set them equal to 0. So that's a fancy way of saying T points in a positive direction, so T. F points in the negative direction, so minus F. And mg sine theta points in a negative direction, so minus mg sine theta. Add up all the forces in the x direction and set them equal to 0. Now I take the next one. Add up all the forces in the y direction, taking into account their direction, and set them equal to 0. Normal points in the positive direction, so n. Mg cosine theta points in the negative direction, so minus mg cosine theta, and set them equal to 0. There, I've done. That's it. That's Newton's laws. That's all they can do. So Newton's laws have created for us 2 relationships. These may or may not be able to solve the problem, but that's all Newton's laws do. So I want to stop there and do 2 things here. First, Newton's laws create a custom equation, one that is made just for this problem. So once you make it here, you've used Newton's laws, but this is custom for this problem. So it'll work on the next problem that has the exact same parameters, but it won't work for a book pushed up against a wall. You're going to have to start over and do Newton's laws again. And it won't work for a person dragging a wagon across the floor. It's going to create a new set of equations for each problem. Now, I don't know if I can solve this, except I do know in the back of my mind, they wanted mu, which is the ratio of friction to normal force. So, I mean, I'm looking here, and I do have something that would allow me to find the frictional force. I could get it by itself, and if I do, I'd get T minus mg sine theta. And I have no trouble leaving like letters here. I don't need to have numbers. If you're desperate for numbers, that's in the problem, but I'm not desperate for it. You shouldn't be either. And I can get n by itself too. So right there, we're done. We've done all the heavy lifting. I got to take whatever this is and put it on the top of this fraction. Whatever this is, put it on the bottom of this fraction, and I have the answer for mu. And again, you won't hear this from me because you're not my student, but I really don't care what the number is. The number is the least interesting part of all this. You guys like the number because it tells you whether you're right or wrong. But to me, that's the least interesting part. Now, the truth is they're going to start the problem over again and say they're going to increase the tension, and they want to know what the acceleration of the system is. You might think that is restarting the problem, but you don't really have to restart the problem. If you're careful, remember, you could reuse this because the parameters of the problem haven't changed that much. We do have one new thing. The tension suddenly got bigger. Is my system still balanced? I don't think it's going to be, because the friction doesn't depend on the tension. So the friction didn't change. The weight, it didn't depend on the tension, so it stayed the same. And the normal force, it was dependent upon the weight, it didn't change. So I think suddenly this is not equal to 0, but it's equal to MA. That's it. I know what the friction is, so that number hasn't changed. I know what the weight sine theta is, that hasn't changed. So yeah, I really don't have to do much here. I just have to change one little parameter, and I can go back and find out now what the acceleration of the system is. So sometimes you luck out like that, and you don't have to redo everything. Yeah, that was a lot of fun. I enjoyed that immensely. I've never done an inclined plane problem like this before. All right, so I'm hit about 2 different standpoints, and I don't know what he's taught you guys to be able to successfully explain to you where I think you should start. So here's what I would tell you to do. Follow the same set of steps we did earlier. If you do that, it's a little more complicated because there's shortcuts here, but I'm afraid that if I start showing shortcuts and not knowing what you guys have learned, then I might distract you from your test. So there's 2 objects here. Because there's 2 objects, 2 dots. That way I can, take a look at the forces acting on each object. So I'm going to start with the 5M object. I always start with the one that's furthest away and work towards the applied force. It doesn't matter which direction I start. I'm just going to do it that way. So I'm noticing that the box has 5M and the other box has 2M. So I'm expecting that it's a longer arrow for the weight for the 5M box. So start with that, 5M. And that means its weight is 5 mg. It's in contact with the surface, so normal force. And here's where things are going to go a little sideways. Although those are balanced, it's in contact with another surface, right? It's touching the other box, but that's still just a surface. So there's a normal force this way. And that is the normal force on box 5 from box 2. So that's why I'm putting 5-2 there to remind me that it's on box 5 from box 2. And that's it. They say there's no friction. There's nothing else acting on this box. So the answer to the question, what pushes the bigger box? The normal force. Box 2 pushes it. A lot of students think this force pushes it, but it doesn't. This force pushes the 2M box, and that's it. So, going on. Elise, I have to make up an FRQ. All right, what are you making up the FRQ for? For which thing?
It was for the Newton's force test, I think.
All right, look, you don't have to be online for that. I'll send it on Canvas, and that way you don't have to sit and wait, okay? Because I'm not here for tutoring, and there's a lot of folks who are here for tutoring, so I don't want to make you sit here and wait, but I also don't want them to be here while I try and rifle through my computer and find it and send it to you, okay? So I will send it over Canvas before I leave to go home tonight, and you can just give it to me sometime tomorrow. Is that all right with you?
Sure.
It's not great, I know, but it's what I can do. All right? Yeah.
Why is it N52 if the force is coming from 2 on 5?
Force on 5 from 2. Would you rather me say force from 2 on 5? I don't care.
Yeah. So wait.
This is the force acting on box 5 from box 2.
Oh, okay. That's what you
So I don't know how else to say it. But that doesn't matter. I put it like that because in a moment, there's going to be a force this way because of Newton's third law, which I'm sure he's talked to you about, right? So if box 2 pushes on box 5, then box 5 pushes on box 2. So whatever I wrote here, this one's going to have to be the opposite. This is the force on box 2 from box 5. They make up a Newton's third law pair, an action-reaction pair. That you have learned, right? So, and like I said, that has to be stated. Now, if you have a different standard for how you write that, then stick with your standard. I don't want to change what Mr. Mosser has told you. I really don't.
He just said it the other, but it's the same thing.
Force from 2 on 5?
Yeah. It's the same thing.
Yeah. That's the thing about prepositional phrases. Do them however you like. Just don't end your sentence with one.
So it's a normal force?
It is a normal force for sure. Force from a surface. It means it's perpendicular to the surface, has to be in the direction of the surface. Because that's, not to try and, screw you over, but, so,
Force of like all the other forces, like gravity and the normal force from the table. Would you have to change both of them to fit the new y-axis?
like for the problem I was just looking at 6 years of grading physics tests and watching people just resort to whatever was the last thing they wrote in their notes. So we're back to this. Let's just get through this. We're going to have a force this way, 2m, force this way, normal from the ground, and this sideways force, F. Now, that's the free body diagram. I don't really have to do a whole lot of work here because I don't have to resolve any forces, but I do have to, again, establish what is going to be, positive, what's negative. And here's where I would start to give you a little bit of caution. When you're doing this, if you really want success, then you need to find a way to be consistent. And who was here earlier? What's your name again? Catherine and I had a conversation about this earlier today. Consistency can be tough because it might go against what your notion of consistency is. So I ask myself, when looking at these problems, how is the motion of this object related to the motion of this object? This one's easy. If box 2 goes to the right, then box 5 goes to the right. So that one's pretty easy. So I want to the right to be the same for both boxes, since they are constrained to move together. And what I mean by that is, I'm going to choose the right to be positive for box 5. So I sure as heck make the right positive for box 2. Need to be consistent. That way, when I recognize that they have the same acceleration, my acceleration for both of them will be in the same direction, because I've chosen that direction to be positive. Now, your book does it different. If you don't like my explanation, use the book's explanation, because it does it a little different. But I do that for pulleys too. So when you have, boy, this is just mind-numbingly dull. We'll keep going with it though. So box number 5, net force equals MA. Box number 2, net force equals MA. Right, they're both second law problems. Right here, this M is generic. I'm just writing down Newton's second law. I say generic because the box on the right actually has a mass of 5m. And the box on the left actually has a mass of 2m. I'm just identifying that this is a Newton's second law problem. I believe the boxes are going to accelerate. Why? Because of this box. It looks unbalanced. And because they asked me for the acceleration. That's usually a big indicator. So I'm going to look at the 5m box first and note that I don't care about the y direction for this one, right? There's no friction, so I don't need that normal force. So N52 equals 5ma. That's it. That's all I can do. So I'm going to look at the other box, and I've got a force to the right, that's positive, a force to the left, that's negative, and that equals 2ma. Questions yet? Any troubles? All right, that's it. That's Newton's laws. They produced for me a custom set of equations that I may or may not be able to use to solve the problem. But that's all Newton's laws can do for me. So now it's the time where I see, can what I have here help me solve the problem? And I think it can. So let's move that over there. Newton's third law tells me that N25 has to be equal to N52. I'm sorry, I put a negative sign, I didn't need to do that. That the magnitude of these two forces are the same. That's Newton's third law. The forces are the same size. I've already indicated that they're in opposite directions. I drew them in opposite directions. So I've already done that part, but I get to say to myself that they have to be the same size. So because of that, I can replace N25 with 5ma. So F minus 5ma equals 2ma. Well, this gives me a way of solving for the acceleration. I hope you see that now, because a is the same for both of them. So F equals 5m plus 2m times a. Now, I'm doing this for a reason. I know that it equals 7. But I want you to stop for a minute and see what is actually here, because there's something here that you might not notice unless I kind of throw it in front of your face. The person on the left that's pushing these two boxes, they don't necessarily know that there's two boxes there. As far as they're concerned, they're just applying a force to a system, to what could be one box. And they're pushing on the side of that one box. From their standpoint, the inertia of this system is 7m. And that's what we have found by looking at the individual forces. We have found that the net force on the system equals the inertia of the system times the acceleration. Every multi-body problem that you have, any one where they're connected by a rope or a string or they're sitting next to each other, eventually, somewhere, you should see the sum of all the masses. If you don't, you've done it wrong. It's going to show up. It has to. The acceleration of the system will always depend on the inertia of the system. So if you don't, by the end of this, see the masses added up, you've done it wrong. Guaranteed. Don't know where you've done it wrong. That means that every one of these, when I look at 16, somewhere there's going to be a 4m in it. Has to be. When I see number 15, somewhere there's going to be 130n. When I see that one on the top, that 2 with the 1, those two boxes, I'm going to have to see the total mass there. I go to that one with box 1, 2, and 3. They have mass 2, 4, and 6. There better be 12 kilograms in there somewhere. And it will always be on the denominator. It determines the acceleration. So it's going to be, when you solve for A, it'll be on the bottom part of the denominator. It's going to show up everywhere. So before you even start these problems, know that you're going to see that in there. It has to be that the inertia of the system determines whether the system will accelerate and how much. So the answer to this question is acceleration is F over 7m. There's more to it too, like what is the force exerted on the smaller box by the larger box? Well, smaller box by the larger box is that sucker, right? Which is the same as this force. So I'm going to use the easier one rather than the harder one. Is that okay with you guys? So I already know that N52 equals 5ma. But I can't use a, I have to use F over 7m. Which is going to be 5/7 F. Which brings me to another thing. Notice 5/7 F. Just notice that it's a part of the total force gets transferred to the other box. Right? I pushed on the first box with F, and part of that force gets transferred to the other box. How much of it? 5/7 of it. Which means 2/7 of the force was used to move the 2m box, and 5/7 of that force was used to push the big box. They will always have to add up to be the total force. 2/7 plus 5/7 will have to equal the total force F. Always has to be. So it's kind of like when you push on a train full of boxes, the force kind of gets divided up amongst all of them. as I continue to say, is I don't really care what the questions are, because the questions don't matter. All of these problems, you start off by looking at how Newton's laws are going to interact with the question, and then hopefully when we're done, it produces something that we can use to solve the problem. So I'm going to go through the same set of steps I went through for the last two questions, because they really aren't any different. The only thing that I'm going to do slight modification here is when I look at this picture, it feels pretty compelling to believe that the system is probably going to move in this direction all around, right? The heavier box is on the right, the lighter box is on the left. There's no chance it's going to go the other way. The only thing that there is a chance of is that it doesn't move at all because of friction. Does that make sense to you guys?
Yeah.
So I will begin the problem by drawing a free body diagram. Luckily for me, they're all going to be very straightforward. So the first one over here, 60 minus tension. I'm going to call this T1. Now you said that the pulleys are massless, which means that all these pulleys do is redirect force. It doesn't take any force for them to turn. That's what massless means when it comes to a pulley. That's not going to be the case the whole year. So for right now, that's kind of nice, but don't assume it's going to be like that all the time. Box 2 is where I'm going to go next, or 2 kilogram box, I mean. And it's got a force of 20 acting down and a force T2 acting up. Now, I've been careful to make sure I drew T2 greater than 20, because I'm pretty confident that box 2, if it's going to accelerate, it's going to accelerate upwards. And I've also been pretty careful to draw 60 greater than T1, because if box 6 is going to accelerate, it's going to accelerate downwards. Good for you guys?
Yes.
All right. That means the box in the middle is experiencing 5 forces actually. It's got T1 this way, T2 this way, friction this way, and wait, he doesn't like stacked arrows, so friction this way, weight this way, and a normal force this way. I believe the whole system is going to accelerate. So I believe this is a Newton's second law problem. Put that up there in the corner to remind me. Okay, so first job is to go through and identify all the forces acting in the system. We have done that. We have identified all the forces acting in the system. We have 3 separate objects. I hope that you guys agree with me that object 6, object 4, and object 2 are linked together in such a way that they all must have the same acceleration. So we can begin employing Newton's laws. Before I do, I need to make sure I have a consistent set of coordinate axes. I don't have to draw a full coordinate axis here. I just need to have kind of a list of what's positive and what's negative. I'm doing that to make sure I have consistency. So, okay, questions about that? All right, here we go. Doesn't matter where I start, so I'm going to start all the way on the left. Net force equals MA, so T2 minus 20 equals 2A. All right, box 4, I've got X and Y, so we'll do the X part first. T1 minus T2 minus friction equals 4A. Good? All right, in the Y direction, Normal minus 40 equals 0. Because although it accelerates in the x direction, it does not accelerate in the y direction. I made sure of that purposefully. Continue? All right. 60 minus t1 equals 6a. There, I've done it. I've used Newton's laws to produce a custom set of relationships that determine how this system behaves. They may not answer my question, but that's all Newton's laws can do for me. However, I have 4 equations and 5 unknowns. 1, 2, 3, 4, 5. 5 unknowns. There must be something else I can bring to bear here. And there is. I know one more thing. Hopefully you know what it is I'm going to say, that friction equals mu times the normal force. Now I have 5 equations and 5 unknowns. We probably want the acceleration of the system. So since that's what we probably want, we got to start eliminating unknowns. We got to start combining equations and stuff. I'll give you a hint. Whatever equation is in the middle, substitute everything into that. It has all the unknowns. Did you notice that? Almost every unknown is in that one. Make that the granddaddy of the whole thing, so that everything is going there. What I mean by that is, and let me give us a little bit of space. Come on, let me do this. It's not letting me do it. I'm trying to shrink it all down, but it's not going to let me shrink it all down. So there we go. If I found the handle somewhere, I could do it. If we look close, I can get this by itself and put it in there. I can get this by itself, put it in there. And I can get this by itself and put it in there. That's what we're going to do. We're going to make that sucker in the middle, the granddaddy of everything. Everything's going to go into that one. So let's start with T1. I've got T1 equals 60 minus 6a. All right, let's get that T2. T2 equals 20 plus 2a. Looking good. Friction is mu times normal force. Normal force equals 40. So friction equals 0.4 times 40, or 16. So I have something for F, something for T2, and something for T1. Let's drop them all into the relationship. So for T1, 60 minus 6a. Minus T2, 20 plus 2a. Minus friction, 16, equals 4a. Notice I dumped everything into the middle because I knew when I did that, I would get one relationship with one unknown, and I've eliminated all of the other variables. Now it's just algebra now, which is not particularly interesting. I'll do the algebra, but it's not particularly interesting. I'm going to do it a way you don't like, though. What I mean by that is I'm not going to do all of the algebra. For the time being, I'm just going to do some distribution. There, I distributed the negative sign. I'm going to get all the stuff with a to one side. So I have 60 minus 20 minus 16 equals 2a plus 4a plus 6a. One thing you should notice is I write everything out. You notice that? I'm not skipping any steps. I'm being meticulous and I'm being thorough. Students get the wrong answer because they try to fit the entire problem the way they would fit it on a line like in a math class. They kind of cram it all together. Just spread your stuff out. Paper's inexpensive, especially digital paper. Just write everything out. You'll make fewer mistakes. But I do want to show you something here. I hope that is coming out. If I factor out all of the A's, you might not see this, but this was the weight of the heavy block. This was the weight of the light block. And this is the force of friction. Those are all forces. In fact, all of this is the net force on the system. There were 3 forces that acted on the system. A block hanging on the right, a block hanging on the left, and friction in the middle. That has to equal the mass of the system. I told you we would see the sum of all the objects in the system somewhere. There it is. This is the system's inertia times A, the acceleration. In any of these multi-body problems, if you've done everything correctly, you are going to see all of the forces that influence the system. You're going to see the inertia of the system, and you'll see its acceleration. And all of these internal forces will disappear and give you what the system is experiencing. Now, I'm pretty sure, Carlos, that you don't need me anymore, right? You can do the math.
Yeah.
That help you out?
Yeah, I did. Thank you.
You're welcome.
That helps a lot.
You guys are going to do great tomorrow. I believe in you.
Thanks.
You're welcome.
Okay.
I appreciate it.
You're welcome, guys. Anytime, and I'll be here again. Just come on over whenever you're ready.
Bye.
Bye-bye.
Thank you.
Oh, the one with the ramp and the pulleys here. There's a box hanging here and a box on the table. I'm going to decide right away that if this box goes down, this box goes up. So this direction is positive and this direction is positive. Why? I want consistency. There is no universe where if this box goes down, this one goes that way. Right? That universe doesn't exist. They are constrained to move together. I want the direction I call positive to be the same for both of them. I have a box that's like this. Oops, not like that. That's not a box. I could have a box like this. And it could butt up against a box that's like this. Right? Well, if I did that, then the normal force here would be in this direction, and the normal force here would be in that direction. It has to be perpendicular to the surface. I don't get to choose the direction here. The surface has determined what direction those forces will be. Okay? I don't know. It really depends on how the problem is constrained to go. If there's a table here, and this whole thing is on a table, well, it's not like these normal forces are going to suddenly cause the object to shoot off the table. So what it probably means is that this force is lifting the box's weight a little bit, which would reduce its frictional force with the table. But that's going to be doing so by burdening this box with probably a larger normal force from the table. That's probably what would happen. But it's not like it's going to change the fact that, the only way these boxes can go is this way or this way. Right? They're constrained to go across the top of the table. So, and I'm just throwing it out there as an example. I'm not trying to confuse you. I'm saying that when it comes to normal force, you don't get to pick the direction of the force. It must be perpendicular to your surface. And this is from with a problem like this. Nope, not a problem like that. Draw this force for weight and this force for normal. 26, I just gave a test. There's one of these on there. No matter how much we try and say the normal force is perpendicular to the surface, students who don't study